Hi all. Today in this video we are going to discuss about algebraic isomorphic structures. So algebraic structures. Any set S, of course S should be well defined, along with one or more binary operations are called algebraic structures. So what are binary operations? They are functions from S cross S to S. So already we have learned about binary operations, their properties and all. So we now learn about algebraic structures, that is any set S with one or more binary operation. Examples are groups, rings, integral domains, fields, vector spaces, etc. All these things we will study in this semester or in the coming semesters. So here what we are going to do is we are going to compare. Usually in our lives we used to compare a lot of things. We used to compare persons, things, salaries, etc. etc. So here we have two composition tables of two algebraic structures. G is set 4 with addition modulo 4, H is S with binary operation star. So first of all, on comparing a composition table, you should look for which is the identity element. So here in this composition table, the same head row is repeated in the first row. So with operating with 0, not much is happening on 1, 2 and 3. So we can easily say that 0 is the identity element. Now coming on to this table, that is H. Here also the head row is almost repeated in the first row. That means operating with A, not much is happening to A, B, C, D. So A is the identity operator here. Now we have to check whether these identity elements are positioned exactly same or not. So here zeros are placed like this, A's are placed like this. Okay, so there is comparison is possible. If identity operators are not, identity elements are not placed in a similar way, then we can easily say that we cannot compare. We can't compare. Okay, so here this ones are here placed and two here B's are placed like almost in the same places, and here twos are placed like this, C's are placed like this, then threes are like in a row, here D's are in a row. So almost I can exactly say that if I am exchanging 0 with A and 1 with B and 2 with C and 3 with D, I can get this table here with this identity operation. Okay, so this identity operation, this two tables are comparable, and I'm getting actually a function mapping Z4 to S. So we will see what is happening. Before that, we will compare two more tables. In this table, here the identity of element is 0. It is placed like this. Here the identity element is E. It is placed like this. So in a different manner. So we cannot compare these two tables. So we'll move on to the definition of the function mapping the 0 to A, 1 to B, 2 to C and 3 to D. I'm saying that this function is an isomorphism. So isomorphism, we know from real analysis classes, it is 1-1 onto homeomorphism and all. Here it is 1-1 onto an homomorphism. So we will move on to each of them. 1-1 means each of the element is mapped with a specific element, because if A and B are same here, then 0 and 1 will be same here. That is 1-1, and on to we know. Now here we are going to study about homomorphism. It is the structure preserving property. The beauty of homomorphism is preserving the structure. Like if I am operating 1 and 2 from the domain, 1 and 2 from the domain, I will get 3. Okay, because addition modulo 4 is the operation. So what homomorphism says is the image of this 3, that is D here, this will be equal to if I am operating the image of 1, that is B, and image of 2, that is C. If I am operating B and C with the operation in the range, that is star, so B star C will be also D. That is the beauty of homomorphism. So homomorphism is that property which adds structural perfection to algebraic structures. So without that, we cannot define and go on with deep study on algebraic, different types of algebraic structures. Now, so 1, 0 is mapped to A, 1 is mapped to B, like that. Now, a sure question for your examination is how to prove isomorphism. So in order to prove isomorphism, what you have to do is you have to prove 4 things. First of all, you have to prove that the phi is a function from S to S dash I am taking. This phi is a well-defined function. So in order to define, or in order to prove that phi is well-defined, I have to take A is equal to B and prove that phi of A equal to phi of B. The second thing I have to prove is phi is 1 to 1. For that, I have to take phi of A equal to phi of B and prove that A equal to B. Then third one is onto condition. We are all familiar with onto condition. That is, for every A dash in S dash, there exists an A in S such that phi of A equal to A dash. Now, our favorite homomorphism property, that is phi of A star B equal to phi of A star dash phi of B. That is, here I am operating with the operation star in the domain, and here I am operating with star dash, the operation of the range. So phi of A star B equal to phi of A star dash phi of B. If these 4 properties are satisfied, then we can prove that this phi is an isomorphism. If there is an isomorphism exists between S and S dash, I can say that these 2 algebraic structures, S star and S dash star dash, are isomorphic, and this is the notation to denote isomorphism. So I think you have followed all the things about isomorphic binary structures. Thank you for watching.